Our guest tonight, who I had the privilege of actually seeing lecture a year ago at the TextFab conference, comes from us from Montreal, Canada, where she's currently teaching at the McGill School of Architecture, and she's also a structural engineer for ARUP. So some of you may have heard about ARUP in your construction courses or read about them before. Maria's field of specialization focuses on computation, parametric design, and digital fabrication. I think over the past few semesters now, we've brought in a lot of architects who are dealing within the same specializations, and we've kind of seen it from their perspective and how they're operating within parametrics and fabrication. So I think tonight is kind of interesting because we'll get a different perspective from an engineering point of view, I hope, and see some of the work that she's doing not only in the office at ARUP, but also in academics working with students. So to highlight a bit on your background, Maria is a senior structural engineer who also has a degree in architecture. She attended UCLM in Spain, where she received her degree in civil engineering and was awarded a scholarship to complete her studies at Imperial College in London. Post-graduation, she has been working for ARUP for many years now, where she has been involved in numerous projects as either the structural lead, a structural consultant, programmer and developer, and recently designer of 2 footbridges to the Aquatic Center by Zaha Hadid at the London 2012 Olympic Park. In 2008, she was sponsored by ARUP for her master's degree in emerging technologies and design from the Architectural Association, or AA, in London. Currently, Maria is a collaborator with the Facility for Architectural Research in Media and Mediation, or FARM, which is a McGill University School of Architecture research hub that aims to unite researchers and students from within the School of Architecture and across the McGill campus with academic, institutional, industry, and professional researchers from around the world. So with FARM, she has been the research lead on a project that completed construction recently called Contemplate, which some of you may have seen this, but you may not have recognized it. It's been featured on many websites from ArcDaily, Architizer, all over the web, also many printed publications as well. And her current project, which she is co-directing, entitled the B-Shack Project. So I hope that we get to kind of see a few images of these, because I think that the 2 projects are interesting because they have some commonalities in the sense that both of them are trying to expose advanced construction techniques, digital processes, and also a theoretical approach to architecture in the public realm. So her lecture this evening is entitled Advanced Computation for Total Architecture. So please join me with a warm welcome, Maria Mingallon.
So that was a lot of talking about me, and it was a great interaction. Thanks so much for doing that. So I'm not going to say much about myself anymore, but I'm going to read this loud up to you. Total architecture implies that all relevant design decisions had been considered together by a well-organized team. This quote is by Sir of ARUP, the founder of ARUP and Partners, the company I work for. And it's really key in the way ARUP designs structures. Now, how do we actually put into practice total architecture? Well, the use of advanced computation tools, it's really key to deliver total architecture. And we are in fact doing nothing that it's really new here. We actually have a great teacher that we all know who has been doing this for many years, and that is nature. Now, natural constructions are actually based on the relationships among the different elements and how these are integrated and their interaction with their environment that they are actually in. And all of this applies to all the different scales in nature. So from the organisms themselves to the actual element, to the actual ways nature creates material. So to the actual microscopic level of material itself. And what I want you to see in this picture is actually the fact that you can't possibly separate form from function and from structure, that the three are really united into one single thing. And it's actually using advanced computational tools that we can actually arrive at analyzing better how this system works and how they're actually constructed and built in nature. Now, the pattern distribution across the wind has actually a lot to do with the way the wind is going to deflect at flight. And as you can see in this video, the hexagonal cells that are actually at the back of the wing are allowing the wing to camber so that it can actually produce thrust and therefore advance while in flight. But the quadrangular cells on the front of the wing are actually there to withstand the strong forces coming from the wind and impacting on the wind itself. So again, geometry, form and geometry in that sense and the structure are not separated, and they're all forming part of the same thing together with function. Now, the use of parametric design tools is actually essential to actually analyze something like this. And it's mainly because parametric design, likewise nature, is not looking at the parameters themselves in an individual basis, it's actually looking at the integration of those parameters and how those parameters are interacting with each other. And that actually makes the model, or converts the model into a dynamic entity, so that it's actually possible to integrate the different design decisions throughout the design process. Now, all of this is very good, it all sounds very good, but then how do we actually deliver total architecture in real projects? Well, tonight I'm going to talk to you about 4 projects in total, where advanced computation has actually been key. And the first one is the Metropol parasol. This is an ARUP project by architect Jürgen Meyer-Hermann. It's located in Sevilla, in Spain, and the ARUP engineer was Jan-Peter Koppitz. Now, as you can see here, is a very complex structure made out of wood. But it was essential that parametric design and digital fabrication were used to deliver this project. It would have been not possible at all to deliver something like this within the budget and the time frame allowed for this project. Just so that you get an idea, it actually took less than a year to erect this on site. Now, this is the actual bit that make that possible. This is the parametric model behind the scenes. The boxes in black are the inputs, the ones in blue are the calculations, and the ones in orange are the iterations. Now what happens here is that we start with certain plate thickness, as low as possible, and we start with a number of bars for the joint type. Okay, so the more number of bars, obviously, the more capacity you have in the joints. But what you want to do is you want to start with the lowest you can, and then work your way through a loop, where what you're going to do is basically you enter that loop, you do your check for the structural capacity, both considering the plate thickness and the joint type, meaning the number of bars. And then if it's not okay, what you do is you upgrade either a thickness or the joint type. Okay, and there has to be a conversation in between those two parameters for which one you upgrade first and which one you do later. And then you you update the loads, because obviously if you're changing thickness and you're changing the joint type, you are changing the loads that are going to act in the system. And then you come back to the loop, and you do this iterative process over and over until you have actually minimized the amount of material that you're using in your structure, but you're actually maximizing the capacity at which the plates and the joints are working. The other thing that I forgot to mention in that slide, which is good about this system, is that you actually can change the catalog of thicknesses and joint types at any time in the process, which is a great advantage to have. This is the structural analysis done in GSA. At ARUP, we actually have our own software that we developed internally. So we don't depend on, well, for some things we do, but for especially structural analysis, we don't depend on big corporations doing the software for us. We actually code it ourselves. We also sell it. And this means that we can actually, personalize, customize our tools. So we ask for the developments that we want in this software, and we get it done. This is a plot of the tensile stresses, and these are the compression stresses. Now you see that some of these elements are actually having high tensile stresses and high compression stresses. It is because these elements, the way they are modeled is as beams, and therefore you know that a beam will actually bend and will have tensile stresses on one side and compression stresses in the other side of the beam. Right? Like that's bending, that's flexure. Now, after all the different iterations, this is the result. There are no drawings that are easy for construction. All the fabricator wants to actually build this thing is this. As crude as it can sound, it's just a spreadsheet from which they are going to fabricate all these different sections and different joints. And only with that data, this KUKA robot can actually start. This is a 5-axis robot which was running for 360 days to cut the pieces for Metropol parasol. And the plates arrive on site together with the steel joints, all these little boxes. Erection starts on site. You can see the dimension and the scale of the parasol. I mean, that's a person right there, and this is one of the start of the columns. Now, they built this temporary scaffolding or platform on top because it was just easier to get your workers up once in the day and then start putting all the pieces together as opposed to having to go up and down with like cherry pickers or scissor lifts or some other construction devices to access. So it's it's one of the things that really comes into play when you do complex structures is this sequencing and the phasing and how you're planning all of that. So even though you're going to be architects and maybe I don't know, maybe some of you actually go into the contractor's side, if you end up doing design, you still have to think about how your thing is getting built, and you still have to think about, is this necessary? Would that be good? Would that be feasible? Would that make it very expensive? All that sort of thinking has to go in there as well. And this is it. The Metropol parasol became real. So there are some images from the top. It actually had a footbridge, mainly for so that people could actually come in here and look at the amazing views of Sevilla. And so, thanks to the use of advanced computation, we actually were capable of adding a lot of value to this project. So we did 3 things mainly, and the first one was minimizing the steel tonnage and the wood tonnage that was used for this project, reducing the number of bars that would have to actually be used on the joints, and most importantly, talking the language of the fabricator, because all we did was transmitting that spreadsheet that I've shown, and that fed all the fabrication process. There were no drawings used for construction or or something in those lines. It was only that spreadsheet that I've shown. And that spreadsheet was actually just the output of all these automated design process. There was nothing else that you actually had to produce. The Wawana sculpture is a piece by artist John Gray, based in Seattle, who actually came to us with a commission he had won to make a sculpture out of the Wawana ship. Now what happened is that the ship was in a very bad state. It was deteriorated and they couldn't really keep it as such. So they decided that with the material that made the ship, with all that timber pieces, that they could actually make something out of it and exhibit it and made people aware of how important historically it was actually the ship. So the artist actually wanted to create something like this. This is photographs of the first set of models that he created, and he wanted something that actually was pending from the roof, or that it appeared as pending from the roof. And as you can see, he also wanted doubly curved surfaces. Now, if you have realized, I have just said that we are going to make this out of 2D planar elements. So in essence, he was asking us to do this out of this. And so, we started to figure out how we were going to actually deliver that. And so what we did, it was actually divide the structure into different pieces and figure out that we actually needed a steel frame that could accommodate the different tapering that was actually that had to happen in the structure. What happened as well is that these panels here, we CNC them, but we had to think about how much we would actually CNC them by, or mill them by, so that they could actually accommodate the tapering both horizontally and vertically. So the dimension of these panels, both vertically and horizontally, was set by how much we could actually mill these panels by. And then they were set on the steel frame, which was also taking care of the tapering so that they look as flush as possible. And they actually ended up looking very flush. And so that's a snapshot of the Rhino model that was used to design this structure. And that's the steel element that I was just talking about. So this was repeated along the length of the sculpture, and it was taking care of the slight taper that was happening from one model to the next one. So basically you're just like trying to make something out of pieces that are completely outside your geometry, but you're doing that by creating a little puzzle that is just fitting through the geometry that you want to ultimately achieve. Now all of this was modeled in Grasshopper parametrically, and the actual CNC G-code was obtained directly from the Grasshopper model. So these are some pictures of the CNC milling while it was taking place. And this is the piece finished. And now this is how the artist actually came into play and started adding his own touch to the piece. So he added these perforations because if you remember, I started by saying that this sculpture was going to be pending from the roof, and so the idea was that there would be natural light that will get through the sculpture and into the building. So how the light actually gets into the building is through these perforations, which the artist is adding, and then what he's doing is he's polishing them off, and you can start to see how nice this structure is really, or this piece is actually getting. So this is the actual piece finished. Quite nice finish. And the installation of the sculpture actually starts. You can see there the steel members that I was talking about before. And also those little notches to make sure that it was fitting flush, that it would fit with this, etc. And so this is it. The sculpture is finished. And again, we are able to add value to this project, not just by being the traditional structural engineer who would have merely sized the members for this sculpture. We actually contributed to the design process and the fabrication process by adding in the ideas on how to make this out of 2D planar elements. And that's what it really added, where ARUP really added value to this project. Now, the King Abdulaziz International Airport is the third project that I'm going to show you tonight. And it's a very good example of the use of parametric design to really bring efficiency into a very large scale building. So the airport roof is actually made out of, we can say, 3 arms. And they have a central roof, which is called the lens, or we call the lens. And when you take a section through one of those arms, this is what you actually get. You get what we call the gills and the lens. Now, the real value of this project is actually in the integration of the parametric design for the space frame, the update or the automation of the loading combination, which get updated every time you change something in the parametric design of the frame, doing that in Visual Basic, the structural design in GSA, and then the sizing of the members. And all of these are truly integrated into an automated iterative design process. Now you're all looking skeptical about all of this because talking about digital and all that sounds very cool, but what are the results? Well, what we did in this project is we actually achieved a 49% savings on the steel tonnage used when compared to the previous scheme that we were given by the client. Now this was done by someone else. I'm not gonna say the company name in here. But I mean, you can compare 370 to 142 and all the numbers, so that adds up to 49% of total saving. Now, this is when contractors really understand the point of parametric design and they don't just see it as, okay, so parametric design is to build up all these net shapes and that's it. It's not, it's actually to deliver efficiency. So, one of the most challenging parts in this project was actually the joints, because you can come up with a very elegant and a very complex arrangement for all your bars and the truss, but you have to deal with the joints because all your bars are going to come at different angles, and how you do that in an efficient way without, really putting at danger the production of the whole scheme because you have all these different angles in your structure, was actually by designing these ball joints in a way that the different angles of the bars that were coming into these joints could actually still connect to them. Now what we did as well is set up an algorithm that in an iterative manner would actually decide on the size of the joints, of these ball joints, and we did that first by checking the interior clashes, but also taking care of the exterior clashes of the bars. So we did this because, as I said before, we were trying to minimize the material used in the joints, but at the same time you have to standardize fabrication. So the more standard joints we would have, the cheapest the fabrication would be. I mean, we all know that. So, and again, in this case, all the fabricator and the contractor wanted was this, just a database of nodes and elements. These were supplemented by a Revit model, but the drawings were still issued in this case. I can't say that there were no drawings, unfortunately. There were drawings, but they were prepared and issued as a mere formality, because in some places, authorities are not really prepared to just not have their set of drawings. Now, this is the last project that I'm going to show you tonight. And this is actually a collaboration with FARM, the Facility for Architectural Research in Media and Mediation in Montreal at McGill University. FARM is funded by Professor Michael Gemtra. And as per the introduction, I do projects outside ARUP, which are collaborations with universities, and in this case, McGill. So the Contemplate pavilion was actually designed with the idea of creating or playing with the perception that you would have from applying a moire effect onto a onto a continuous strip, into a continuous surface, such as the Mobius strip. So the pavilion was designed as an irregular truss, which was actually set in between the two layers of the moire effect. Now, when I say irregular, I really mean it, because it's really not a standard angles or anything like that. And we were able to do this because all our angles or our joints were actually CNC bent. So we actually had all of the bolts, all of the bars, all of the moire elements. Everything was designed, was actually done in Grasshopper, so was modeled well ahead in Grasshopper. And what you see here is a snapshot of the Rhino. And this really was very helpful to identify possible clashes and to actually resolve them well early in the process. But it also helped when we had to actually make changes to the geometry, because we were feeding in the actual instructions from the structural model, or because we wanted to change something because of the architectural program itself. So this is a photo showing the CNC'd mill ribs, where you can actually see little numbers right here. Now this indicate the location where the moire elements are going to be connected to. And these were all CNC by the students at the school. I mean, the whole pavilion was actually assembled by students. There were no professional contractors or anything like that. And these are the steel joints that I was just talking about. Now, all these angles are different completely. But we were lucky enough that we had this because we could CNC bend all these angles. Now, again, there were no drawings for the construction of this project. What we did, it was building up in the naming convention the way the things were going to be put together. So you would know which piece goes with which without having a drawing next to you. I mean, in that sense, it's a little bit of like a Lego type approach. And yeah, as I said, there were no drawings, it's the 3D model, and that was it. Now I'm going to show you a video which I hope you like. This is going to wrap up the session, so I'm going to finish with this video. It's going to show the construction sequence of the pavilion. So just going to set it there. That's it. Thank you. Yeah.
I have a question. Thank you, Maria, for your presentation. Could you talk more about the relationship between the engineer, the architect, or the designer, and actually how the two are nurturing each other or challenging each other, or is the project changing after this relationship is growing or developing, or?
Okay, it's a good question, and it's a question that over coffee or over a glass of wine is really the perfect question. And it's difficult to say because it really depends on the project. At least that's my experience. There are projects where you can't really separate the architect from the engineer that much. Like the two really have to work together, and I think the ones that I have chosen to show tonight are really that type of project. So in the parasol, there wasn't this like, okay, you're the architect and I'm just making it work type thing. It was a true communicative process in between the architect and the engineer. But I think it all comes down to, both parties knowing a little bit more of what the other one is supposed to be doing and what you want to get out of it. And it's true that in other projects, a lot of architects and a lot of engineers tend to just do their little thing. So they sit in the silo and they say, well, I just want this out of you, so just give me this and I'm gonna run with it and I'm not gonna make any questions. I think the best architects that I have met are the ones that actually challenge every single thing that I would say to them, and they challenge it because they know what I would be talking about. And I would also, in that sense, I would also understand where they're coming from because of my background in architecture as well. So I wouldn't just be like, okay, I close my door and this is the answer and that's it. I would tend to be much more cooperative than that, and I think engineers at ARUP are genuinely like that. And I have to say, I think all of that comes in because our founder really built up, that spirit. Because he was an engineer known for collaborating with the architects at the time and really understanding structural design as this, total architecture concept, that it doesn't have to be just sizing the member, but much more than that. That the structural engineer can actually contribute much more to the building, and the architect in that sense can also make a building that is exactly what he or she wants. So, is that, yeah?
Last question.
Okay.
So numerous times you mentioned that there were no drawings produced, only spreadsheets and a three-dimensional model. That's interesting to me on many levels, both in terms of the deliverables about what a client or what a project needs. But I'm interested in thinking about it in terms of a process, like before the end product, but the drawing as pictures, not necessarily, but the instructions, whether they're graphic or written, is really what it's about, right? And so there's different ways to get to the instructions, and how that develops along the way. Is it? Because it sounds like a statement about. It reminds me of Columbia saying we're not going to do a paper anymore. We're only going to do things in the computer. And I have a hard time believing that it's that rigid, given the dexterity of the work that you all do. And so,
yes and no. I guess we're at that point where the living without paper can actually start to happen, but it's of course hard to change the mind of people. I mean, like authorities are not going to be up to it for a long time.
I mean, even just before it goes to anybody, authorities or client, as you're developing something, what various forms of media do you use as an iterative process?
Right. So what I meant. So of course we will produce sketches. Okay. perhaps drawings. But what I meant is that, you know, like typically you have to go through the different processes when you do a project. So the first one will be getting your approval, so to make sure, like, all the permits and everything, to make sure you can actually build the project. Then you'll have to go through an external check and have an independent engineer actually verifying your project and stamping it, saying yes, this can go. And then you actually do several reviews. Like, that actually doesn't really happen effectively like that. It goes through several reviews where you update the drawings and so on, and then you use your drawings for construction, right? And so that's all very good, but that's serving a part of the population that that work like that. But then when you come to build something, I found that a lot of times something that is in a drawing, it was very good because someone drew it in 2D, but things are 3D. You know, we build things in 3D, when we can't change that. And there were a lot of times where I had to go through the process of, you know, making changes to these drawings and reasoning them again because they were wrong. And there won't be drawings that I would have designed myself, so I would have to, you know, still deal with all the grief from the contractor for something I'm not even to blame for. But so in that sense, yes, of course, I'm not saying that, you know, we don't do sketches or that we don't even use paper. That's not the point. But the point is that a fabricator doesn't care about the drawing that much. I mean, all they need to make their machines work is the coordinates of literally the actual G-code that is going to drive the machine to come up with those shapes. That's all they care. And so to them, you know, they need data, and they need that data digitally to be able to input it into those machines. The paper might be informative, might serve as a secondary means of, you know, getting things through, like, okay, you look at it and you understand what you have to build. But you're not going to be building out of those drawings, not for projects like this. Is that, yeah?
So in that scenario, the drawings are more representative than they ever have been, in terms of they're truly representation rather than involved in the process of construction.
Yeah, exactly. Yeah, and I think, you know, as I said, I don't know, I wish I could actually live long enough to see it happening, to see the true no drawings happening.
Pure data.
Yeah, pure data, and that's the actual deliverable. And more often, you actually get in the contract clauses that ask you to deliver the Revit model. And you do specify, you know, all the different things that the Revit model must have, like all the table of development and all that thing, because of course you can deliver a Revit model that is actually not meeting all the criteria. But that's the sense to me. In essence, that is saying that we are going towards that, you know, towards that path. I'm not saying you're not gonna still do a hand sketch, you know, when you need to. I think it's a very natural human thing to do. Even people that are not architects or engineers would draw, right? So I'm not saying that that's just like going to disappear. But I do think that people will realize that the validity and the usedness of Revit model is, or you know, a 3D model is much more than having drawings these days. Yeah.
Over the past few years, I've been more interested in polymer plastics. Mm-hmm. Specifically for structural purposes. Mm-hmm. And I know you've done a few things with alloys.
Yeah, with shape memory alloys.
Where do you feel that's going, like, as far as the future goes, for structural purposes, rather than simply aesthetical?
Right. You mean the fiber composites? Mm-hmm. Okay. So there are actually a lot of products today that are manufactured for building purposes that are done with GRP, like glass reinforced polymers. And you can find them in, well, both in the buildings and in the infrastructure industry as well. Like, I know that they've been used for bridges, and they have been actually small span bridges fabricated in fiber composites. So in that sense, I think, you know, fiber composites are probably the replacement of concrete, in a way. The problem is, whenever you do a jump like that in the industry, you know, you have the concrete and steel industries, they're very well nailed to the ground, so it's going to be difficult to actually shift them. And in the construction industry, things don't tend to shift that much in a short period of time. You know, like reinforced concrete got started to be used in the 60s, and now it's like everywhere. Like now, reinforced concrete is something no one really even wonders about it. You know, it's like for granted. Now, ARUP was actually one of the precursors on the use of reinforced concrete, and at the time, everyone thought that he was completely crazy. But reinforced concrete was actually giving him the opportunity to reduce the sections much more than if he was just using concrete itself, right? Because concrete in compression is very good, but in tension it really has like about, you know, if you have like a 35 MPa concrete, you have about 3 MPa tensile resistance, so it's nothing, and so it would crack and all of that. So in that sense, you know, I see that fiber composites are starting to be used, and they are you know, going somewhere, but again, I think that there is a huge need for architects and engineers to demand more from the industry. And I think that's when you actually get that shift, you know, like if you are well instructed architects and you go out there and you practice, and then you're not just going to take things for granted, you're gonna explore and test more things, then that's when the industry can actually shift and deliver other things. So does that answer your question?
Going back to the last project you showed, whenever I saw the 2 different connections, joint connections, whenever in the design process or the construction process, did those joints come before the generation of the form of the pavilion or after?
Was that for the Contemplate?
Yeah.
Or right? So for the Contemplate, the joints came after the shape was actually decided, but they were all the time informed. So in that sense, you know, the bars were not static. Like they were not just. They took many configurations until we actually worked out that the geometry that they are following right now is the actual is the good one. And so that was informed from the structural design quite a lot. But also from the program itself. So in that sense, there were a lot of times where there were bars that in the spatial truss, they were doing something that structurally I would not necessarily want, just because of efficiency purposes, and you know, because the pavilion actually had a cantilever, like this structural truss that was rotating in the space in between those 2 layers of the Mobius strip, had a cantilever of about 6 meters. So, so in that, in the middle part of the cantilever, we wanted to make it as thin as possible, while the back had to have much more structural depth to pull back, right? To pull back the pavilion itself. So, yes, the joints in this case came, let's say, after all of that process was going on, but it wasn't really like, you know, we decide on the shape and that's it, and then we go and just get it done. There was a lot of iteration in between the team until we actually get to the shape that we thought it was the most efficient one in that sense. Now, in the like in the other example, in the airport example, the joints were actually something that was thought after the process of coming out with the layout for the space frame, but they were shaped in such a way that you could still fit in all the different bars. Because you know, what happens is that you might want to do all those joints with those angles, right? But then there is it has to be a back and forth conversation where you actually shape the joints so that they don't become too expensive, or that you make sure that you can actually fabricate those joints.
So at that point, standardizing the joint didn't impede the design to go through or to remain the way it was. So standardizing the joint actually became efficient for the structuring and building the airport.
Yeah, right. So exactly. So making sure that the joint was a standard. I mean, when I say a standard, there were different types of joints, but they were grouped, right? So, and they were grouped, and each of them could actually have different different locations for the bars to connect to. I can show. We go back on this. We'll have to go a little bit back. So this is just like one of the joints that was used, okay? There were more. But what you can see here is that even this joint is gonna be able to take bars in the different spots here. So they'll have different angles that are coming to the joint, and therefore you can actually, in a way, like mass fabricate customized structure or customized architecture. Because what you don't want is to lose the efficiency on the space frame, because you can't build something. Like building your stuff is what you are gonna, you know, have to go through. It's not easy because everything stands in a piece of paper. But to make it real and to make it real in the way you want, these are the sort of things that you'll have to go through. It sounds like fun.
Well, if there's no other questions, let's